Two theories run your world, and they cannot both be true. One bends starlight, corrects the clocks above your head by 38 millionths of a second every day, and has not missed a prediction in 110 years. The other, built the device you are listening to, agrees with experiment to 1 part in a trillion, and has never missed either. Perfect, twice over. And yet they flatly contradict each other about what reality is. Not inside a black hole, not at the Big Bang, on an ordinary tabletop, at the mass of a speck of dust, where the oldest trick in gravity, falling, quietly stops working. Something has to give. By the end of tonight, you will know which of the two greatest theories in science, one of the world's most decorated physicists, says is actually wrong. And it is not the one you expect. Before we begin, if you like ending your day with reality gently taken apart, a quick like or subscribe genuinely helps me keep making these. It is a small thing, and it means a great deal. Now, let's ease in. Physics has never been wrong twice in the same century, and that is exactly the problem. Somewhere in the world tonight, a physicist is using one theory to calculate the orbit of a satellite, and another theory to design the chip inside the phone that receives its signal, and both calculations will come out right, to more decimal places than any human being will ever need. And yet those two theories, the two most successful descriptions of nature our species has ever produced, flatly disagree about what the universe is. They cannot both be exactly true. One of them, at some level, has to break. Tonight, slowly and carefully, we are going to find out which one, and the answer, defended by one of the most decorated physicists alive, is probably not the one you expect. Let us begin with the scorecards, because the scale of this problem only makes sense once you understand that neither theory has ever lost. The first is general relativity, Einstein's theory of gravity, completed in 1915. It says that space and time are not a fixed stage, but a flexible fabric, curved by matter and energy, and that what we call gravity is simply things moving through that curvature. It is a strange idea, and for over a century, nature has agreed with it every single time we asked. Consider what that record actually looks like. For decades before Einstein, astronomers knew that the orbit of Mercury drifts in a way Newton's gravity could not explain. A slow rotation of its oval path amounting to 43 seconds of arc per century, an angle so small it is like watching a clock hand creep by the width of a coin held several kilometers away. General relativity predicted that number exactly, with nothing adjusted and nothing added. In 1919, astronomers measured starlight bending around the darkened sun during an eclipse, and it bent by the amount Einstein said it would. And the theory is not a museum piece. It is running in your pocket right now. The satellites that provide GPS carry clocks that tick faster than clocks on the ground, because they sit higher in the Earth's gravitational curvature, and the difference, about 38 millionths of a second per day, sounds like nothing until you learn that without correcting for it, your map location would drift by roughly 10 kilometers every single day. Navigation would collapse in an afternoon. The theory has passed harder tests than that. In September of 2015, two enormous detectors in the United States felt space itself stretch and squeeze as a ripple passed through the Earth, a gravitational wave, launched by two black holes that collided more than 1 billion light-years away. The instruments registered a distortion about 1/1000th the width of a proton. Einstein's equations had predicted the existence of those ripples 100 years earlier. The waveform that arrived matched the prediction like a signature, and in April of 2019, the theory sat for its portrait. An alliance of radio telescopes spanning the planet, a virtual dish, effectively the size of the Earth, assembled the first image of a black hole, the supermassive object at the heart of the galaxy M87, a ring of superheated matter around a darkness 55 million light-years away, with the ring's size and shape matching Einstein's equations to to within the measurement's precision. Think about the arc of that record for a moment. A theory conceived before television, before antibiotics, before most homes had electricity, predicted the silhouette of an object 7 billion times the mass of our sun in another galaxy, and when our species finally built an instrument capable of checking, the silhouette was there, as drawn. In 110 years of trying, across 60 orders of magnitude in scale, nobody has ever caught general relativity in an error. That sentence deserves its own silence. Now set that theory aside, gently, and pick up the other one. Quantum mechanics is the physics of the very small. Atoms, electrons, particles of light. Assembled in the 1920s by a generation of physicists who were, by their own accounts, half convinced they were going mad. It describes a world where objects do not have definite properties until measured, where a single particle can travel two paths at once, where the fundamental language is not certainty, but a wave of possibilities, and its scorecard is, if anything, even more absurd than relativity's. Quantum theory's crown jewel is a number called the electron's magnetic moment, a measure of how strongly an electron behaves like a tiny magnet. The theory predicts this number through a long and delicate calculation, and experiment measures it through a long and delicate procedure, and the two agree to roughly 1 part in a trillion. Let me give that number a body. Measuring something to 1 part in a trillion is like measuring the distance from New York to Los Angeles and getting it right to within the width of a single human hair. No prediction in the history of science has ever been confirmed more precisely. And like relativity, quantum mechanics is not an abstraction living in a journal. It is the reason the device playing this video exists. Transistors work because electrons obey quantum rules. Lasers, LED lights, MRI scanners, atomic clocks, the entire discipline of chemistry, all of it rests on quantum mechanics being correct about how matter behaves. The theory has been interrogated for 100 years by the most precise instruments ever constructed, and it has never once been caught in an error. So here is where we stand. We have one theory of the large: planets, stars, galaxies, the shape of the universe itself, that has never failed. We have one theory of the small: atoms, electrons, light, that has never failed. A reasonable person might conclude that physics is nearly finished, that we hold the two halves of the answer and need only staple them together. And that is precisely where the trouble begins, because the two halves refuse to be joined. They are not two chapters of one book. They are written in different languages, about different worlds, resting on assumptions that contradict each other at the root. Let me give the disagreement its plainest face before we give it its technical one. Ask general relativity what the world is, and it answers: a four-dimensional geometry, smooth and continuous, where everything has a definite place and a definite history. A single, sharp, curved reality. Ask quantum mechanics the same question, and it answers: a catalogue of possibilities, humming along together, none of them definite, until something, and the theory is notoriously silent about what, forces a choice. One theory says the universe is a shape. The other says it is a maybe. These are not two dialects of a common tongue. They are answers to the question, what is real, that cannot both be the final word. The contradiction is not a matter of taste or interpretation. Quantum mechanics is built on a rule called superposition, which says that any two allowed states of a system can be added together into a new allowed state, a particle here, a particle there, and, legitimately, a particle in both places at once. General relativity is built on a rule called the principle of equivalence, which says that gravity and acceleration are locally the same thing, and that falling freely erases gravity from your world entirely. Each rule is the load-bearing wall of its own theory. And as we will see tonight, there is a simple, almost embarrassingly ordinary situation. A small object, a table, the Earth's gravity. in which those two rules issue instructions that cannot both be followed. Not in a black hole, not at the beginning of time, on a tabletop. Most physicists, for most of a century, have handled this the way a family handles an old argument at dinner, by keeping the two relatives at opposite ends of the table. Gravity is so feeble at the scale of atoms that you can almost always ignore it in a quantum calculation, and quantum fuzziness is so tiny at the scale of planets that you can almost always ignore it in a gravitational one. The two theories rarely have to speak, but rarely is not never, and a contradiction that can be avoided is still a contradiction. If the universe is one thing, and every observation we have ever made suggests that it is, then somewhere beneath these two perfect theories lies a deeper truth, and at least one of our masterpieces is an approximation of it. The question that will carry us through tonight is which one gives way, the theory of the large or the theory of the small, Einstein's space-time or the quantum wave. There is a man who has spent decades arguing for an answer, and his answer is the reason this question has teeth. He is one of the most credentialed physicists alive, a Nobel laureate whose theorems reshaped our understanding of black holes, and his verdict is blunt. The theory that has to break is not Einstein's. It is quantum mechanics, the one with the perfect trillion decimal scorecard, the one running the device in your hand. He believes its central equation is not the final law of nature, but a superb approximation, and that the thing which exposes it is gravity itself, working quietly at a scale no experiment has yet reached. We will meet him properly in due course, and we will walk through his argument step by step, because it is one of those rare arguments in physics that a listener can genuinely follow all the way down. But an argument like that cannot land on an empty table. Before the collision, we need the towers, both of them, built honestly, at their full height, so that when they grind against each other, you feel the weight of what is grinding. And the older tower begins in the most unlikely place imaginable, not in an equation, not in a laboratory, but in a very old observation about what happens to things when they fall. It begins, if you like, with a burst of fireworks over an Italian evening, 400 years ago, and with a secret hidden inside that burst which almost nobody who has ever watched fireworks has noticed. Every deep idea in physics has a birthplace, and the birthplace of general relativity is not where you would think. It is not the patent office in Bern, and it is not the blackboards of Berlin. It is a simple observation about falling, one so old that it predates telescopes, so gentle that it hides in plain sight at every celebration on Earth. To understand why Einstein's theory of gravity is built the way it is, and why its foundation will matter so much when the collision comes, we need to go back 4 centuries to a man watching things fall and noticing what everyone else had missed. Galileo Galilei understood something about gravity that took the rest of the world 300 years to fully appreciate. Gravity treats everything exactly the same. Drop a cannonball and a musket ball from the same height, and setting aside the resistance of the air, they land together. Not approximately together. Together. The legend says he demonstrated this from the Leaning Tower of Pisa, and the legend may be embellished, but the insight is documented and genuine, and Galileo himself reached for a more beautiful illustration than any tower. He described fireworks. Picture it now, because this image is going to travel with us for the rest of the night. You are standing in a dark Italian piazza, 400 years ago. The evening smells of smoke and river water. A shell goes up with a hiss, a thin orange thread climbing the dark, and then it bursts. A perfect sphere of sparks, blooming outward in every direction at once. Hold your eye on that sphere. It is falling. The whole formation, hundreds of burning points, is dropping toward the rooftops. And yet the sphere remains a sphere. It does not smear. It does not stretch into a teardrop as the heavy sparks outrun the light ones. Every spark, whatever its size, whatever its weight, falls at exactly the same rate as its neighbors, so that relative to one another, the sparks are not falling at all. They are simply drifting apart in a slow, widening bloom, as if gravity did not exist. From inside that sphere, if you could ride one of the sparks, you would see your companions floating around you, serene, weightless, going nowhere. The ground rushing up is the only clue that anything is happening at all. Galileo saw that, and he wrote it down. The burst keeps its shape as it falls. 4 centuries later, the sphere of falling sparks is still the cleanest picture ever offered of the deepest fact about gravity. Fall with it, and it is gone. Stay in the piazza one moment longer, because there is a second thing to notice, quieter than the first. Look at the crowd around you, the faces tipped upward, lit in pulses of orange and gold. Every one of them is watching the same sphere, and not one of them is seeing it. They see beauty, spectacle, an evening's entertainment. 400 years of humanity will watch this same falling bloom at festivals and harbour fronts and midnight celebrations. And in all those centuries, on all those upturned faces, almost no one will ever notice that the deepest law of gravity is performing directly overhead, in plain view, disguised as a pretty shape. Nature does not hide its foundations in distant galaxies. It hides them in things too familiar to question. Hold on to that thought tonight, because it is the method of our entire journey. The biggest cracks in physics are not out there somewhere. They are in the falling of sparks, the ticking of clocks, the settling of dust, the places nobody thinks to look, because everybody has already seen them. That fact has a name now. We call it the principle of equivalence, and it says that falling freely is locally indistinguishable from floating in empty space, and that standing in a gravitational field is locally indistinguishable from accelerating upward in a rocket. Gravity, in other words, is not like any other force. You cannot feel it. What you feel when you stand on the floor is not gravity pulling you down, but the floor pushing you up, interrupting the fall you would otherwise be in. An astronaut in orbit is not beyond Earth's gravity. At the altitude of the space station, gravity is still about 90% as strong as it is on the ground. The astronaut floats because the astronaut is falling, continuously, around the planet, along with the station and everything in it. One more spark inside one more sphere. Albert Einstein arrived at this insight in 1907, while working at the patent office in Bern, and he later called it the happiest thought of his life. The thought was this: a person falling freely from a roof does not feel their own weight. While they fall, gravity, for them, has simply switched off. Tools dropped alongside them would float in their company. Einstein realized that this was not a curiosity, but a key. If falling erases gravity, then gravity cannot be a force in the ordinary sense, some invisible hand gripping objects and hauling them down. It must be a feature of the arena itself, of space and time, something you can locally cancel just by moving the right way, the way the sparks cancel it inside their sphere. It took him 8 more years to build the mathematics, and the mathematics changed what the universe is. In general relativity, completed in 1915, matter and energy curve the fabric of space and time around them, and objects in free fall are not being pulled by anything. They are doing the most natural thing possible, moving in the straightest available line through a curved geometry. The Earth orbits the Sun, not because a force tethers it, but because the Sun has bent the space-time around itself into a shape in which the Earth's straightest path is a loop, the way the straightest path an airliner can fly on our curved planet traces an arc on a flat map. The falling sparks keep their sphere because every one of them is following the same curvature, and the curvature, unlike a force, does not care what anything weighs. One honest fine print belongs on the Mercy, and it will matter later tonight. The erasure of gravity by free fall is local. It works perfectly at a point, and very well in a small region, but it cannot be stretched over a large one. A falling elevator the size of a continent would betray itself. Objects on its far sides, each falling toward the center of the Earth, would drift measurably toward each other, and the tides of that drift are curvature's true signature, the part no single act of falling can remove. Physicists say the equivalence principle holds locally, and the word is not a lawyer's hedge, it is the exact shape of the promise. Fall, and gravity vanishes here, in your immediate patch of the world. Keep the phrase in your pocket. Before the night is over, we will meet a situation where even that modest promise, one patch, one fall, one erasure, cannot be kept. Notice what kind of theory this is, because the character of it matters for where we are heading. General relativity is geometry. It is smooth, continuous, and deeply nonlinear. The curvature shapes how matter moves, and matter shapes what the curvature is, each feeding back into the other, in an endless conversation. There is no fixed stage. Space and time are performers in the play, not the theatre it happens in. And the principle of equivalence is not a decoration on this structure, it is the foundation stone. The entire edifice stands on the claim that free fall locally erases gravity, that you can always, anywhere, climb inside the sphere of sparks and watch gravity vanish. Remove that claim, and the geometry has nothing to stand on. Keep it in mind. Tonight, we are going to meet the one object in physics for which the trick fails. The world, it should be said, did not immediately kneel. When Einstein published, plenty of physicists said he was wrong. Saying Einstein was wrong is not a modern hobby. People were saying it before most of our grandparents were born. What silenced the doubters, at least about this theory, came in May of 1919, when the astronomer Arthur Eddington led an expedition to measure the position of stars near the darkened sun during a total eclipse. If the sun curves the space-time around it, then starlight grazing its edge should bend, shifting those stars slightly out of place, by 1 3/4 seconds of arc, roughly the angle of a coin seen from kilometers away. The plates came back, the measurements were made, and the stars had moved by Einstein's amount. The result ran on front pages around the world, and a patent clerk's happiest thought became the most famous idea in science. There is an irony buried in that fame which will make you smile a little later tonight. When the Nobel Committee finally honored Einstein, in the early 1920s, they carefully avoided giving him the prize for relativity, which was still considered too controversial. They gave it to him for something else, a piece of work from 1905 that helped ignite a completely different revolution. We will come back to that, because the other revolution is the other tower. For now, stand back and look at what we have built. Gravity, the most familiar force in your life, the one that has held you to this planet since before you were born, the one your body is negotiating with every time you take a step, turns out not to be a force at all. It is the shape of the world, and its deepest law is a kind of mercy, fall, and it cannot touch you. Every satellite we have ever flown, every planet we have ever tracked, every black hole we have ever imaged has obeyed that law without exception. The tower is perfect. Nothing in 110 years has put a scratch on it. But while Einstein was bending space, another group of physicists, some of them his friends, one of them effectively his heir in the Nobel records, was discovering that the small world does not merely bend the rules, it replaces them. The second tower is stranger than the first, and its foundation is a principle that sounds less like physics than like a riddle, that a thing does not have to choose what it is. To build it, we need to leave the piazza and the falling sphere of sparks and walk into the one place where even Galileo's mercy has never been tested, the world inside the atom. The second tower was not built by one mind, and it was not built on purpose. Quantum mechanics was assembled between roughly 1900 and 1927 by physicists who kept trying to patch the old physics and kept discovering that the patch was bigger than the garment. Max Planck introduced the quantum, the idea that energy comes in discrete packets, as what he called an act of desperation, a mathematical trick to fix a formula about glowing hot objects. Einstein, in 1905, took the trick seriously and proposed that light itself comes in packets, particles we now call photons. That is the work the Nobel Committee eventually honored, which means the man whose gravity theory we are about to defend won his prize for helping found the theory we are about to put on trial. History has a sense of humor about these things. By the middle of the 1920s, the patches had become a new physics, and at its heart sits an equation written down by Erwin Schrödinger in 1926. The Schrödinger equation is the law of motion for the small world. Where Newton tells you how a planet's position changes over time, Schrödinger tells you how something called the wave function changes over time. And the wave function is one of the strangest objects ever admitted into science. It does not tell you where the electron is. It tells you, for every place the electron could be, a quantity whose square gives the probability of finding it there. The electron, between measurements, does not have a location. It has a spread of tendencies, a wave of maybes, flowing through space, according to Schrödinger's rule, as smooth and lawful as any tide. Here is the feature of that law that tonight's entire story turns on. The Schrödinger equation is linear. That is a technical word with a plain meaning. If the equation permits one history, and it permits a second history, then it permits the sum of the two, both at once, overlaid, like two transparent photographs stacked on a light table. Physicists call this the principle of superposition, and it is not an optional flourish. It is the load-bearing wall of the entire quantum edifice, exactly as the principle of equivalence is the load-bearing wall of Einstein's. If an electron may pass through the left slit of a barrier, and may pass through the right slit, then the equation insists it may do both together, and the famous striped interference patterns of the double-slit experiment, which we have walked through on another night here, are the fingerprints of that bothness, recorded by the billions in laboratories for a century. A particle of light may be polarized this way and that way at once. An atom may be in its resting state and an energized state at once. The mathematics does not merely tolerate these combinations. It generates them constantly, promiscuously, as its default behavior. Notice how different this tower's architecture is from the first one. General relativity lives in 4 dimensions, 3 of space, 1 of time, and it is non-linear to its bones. Curvature begets motion begets curvature, and you cannot simply add 2 solutions together to get a third. Quantum mechanics is the opposite temperament in every respect. Its wave functions live in an abstract arena called Hilbert space, which is not the space you walk through, but a space of possibilities. And that arena can have any number of dimensions, thousands, millions, infinitely many, without the theory blinking. Roger Penrose, whom we will meet properly soon, has a wry way of putting it. Quantum theory is delighted by infinite dimensions, but every one of them is flat. Flat as a pancake, in his words. No feedback, no curvature, no conversation between the stage and the actors. Just the serene, linear addition of possibilities, forever. One theory says the world is a curved geometry that everything shapes and everything feels. The other says the world is a flat, unbounded ledger of alternatives that simply add. Hold that contrast. It is not yet a contradiction, but it is the temperament of one, waiting. If the flat ledger were merely a bookkeeping curiosity, none of this would matter. What makes it eerie is that the ledger's overlaid entries push on the world. When possibilities overlap, they interfere, reinforcing where their rhythms agree, cancelling where they clash. And the interference leaves marks that single, definite histories could never leave. The stripes of the double slit are such marks. So is the shape of every atom. Electrons in atoms do not orbit like planets, but exist as standing waves of possibility, and the geometry of those overlapping maybes dictates which atoms bond to which, at what angles, with what strength. Which is to say, the ledger's arithmetic decides the architecture of every material thing, including the body you are resting in. The maybes are not decoration on reality. As far as the equation is concerned, they are the machinery of it. And yet, this is the part that keeps honest physicists awake. The strange, flat ledger works. It works beyond any reasonable standard of evidence ever applied to a human idea. We have already met the crown jewel, the electron's magnetic moment, predicted and measured in agreement to about 1 part in a trillion, the distance from New York to Los Angeles, known to the width of a hair. But the scorecard goes so much further. Quantum mechanics predicted the existence of antimatter before anyone had seen it, out of pure mathematics, when Paul Dirac's equation insisted on a mirror twin for the electron. The positron was found in the debris of cosmic rays a few years later, exactly as ordered. It explains why the periodic table has the shape it has, why some materials conduct and others insulate, why the sun shines. Hydrogen nuclei in the sun's core do not have enough energy to fuse by classical rules, and they fuse anyway, because their wave functions overlap through a barrier no classical particle could cross. Every time you have ever felt sunlight on your face, you have been warmed by superposition doing something impossible. The antimatter story deserves one more beat, because it shows the ledger doing something almost arrogant. When Dirac unified quantum mechanics with special relativity in 1928, his equation developed what looked like a defect, solutions with negative energy that refused to go away. A lesser physicist would have amputated them. Dirac, after wrestling with the mathematics for years, proposed instead that the defect was a discovery, that every particle has a mirror twin, identical in mass, opposite in charge. He was proposing a new half of the universe because an equation insisted. In 1932, Carl Anderson photographed a track curving the wrong way in a cloud chamber, the anti-electron, exactly as the mathematics had demanded. The ledger had predicted the existence of a kind of matter no human had ever conceived, sight unseen. That is the caliber of theory we are dealing with, and the caliber of theory we will be asking before tonight ends to confess to being wrong. The technology scorecard is, if anything, more intimate. The transistor, the tiny quantum switch at the heart of every computer, exists because engineers learned to sculpt the wave functions of electrons in silicon. There are billions of transistors in the device playing my voice right now, and every one of them is a small monument to the accuracy of the Schrödinger equation. Lasers run on quantum rules. The MRI machine that can photograph the inside of your knee runs on the quantum behavior of atomic nuclei in your own body. Atomic clocks, the ones correcting for Einstein's time dilation in the GPS satellites, in one of the quiet ironies of modern engineering, keep time using the quantum vibrations of cesium atoms, and they are accurate to about 1 second in 100 million years. A century of interrogation by the most sensitive instruments our species has ever built, and the flat ledger of maybes has never returned a wrong answer, not once. So we should say it plainly, the way we said it of Einstein's tower. This theory is perfect, as far as any test has been able to see. And now let the night's central tension begin to surface, because there is something buried in that perfection which does not belong there, a smell of smoke in a house with no fire yet visible. Look again at what the Schrödinger equation actually says. It is smooth. It is deterministic, given the wave function now. It dictates the wave function forever after, with no dice anywhere. And it is linear, which means superpositions, once born, never die. The equation contains no mechanism, none, by which a wave of possibilities ever becomes one actuality. Left to Schrödinger's law, the electron that went through both slits should go on being in two histories, and the detector that measures it should enter a superposition of recording both, and the physicist who reads the detector should enter a superposition of seeing both, and so on, outward, without limit, and without end. Nothing in the equation ever chooses. And yet, look around you. The world has chosen. The lamp in your room is on or off, not both. The book fell open to one page. Your body is in one bed. Every measurement ever performed in every laboratory in history has yielded exactly one outcome. Somewhere between the electron and your eyelids, the bothness that the perfect equation demands, and demonstrates daily in the small world, quietly disappears, and the equation does not say where, does not say when, and does not say why. There is a missing verb in the most accurate law of nature ever written. The law describes everything except the one thing that always happens. For 100 years, physics has lived with that missing verb by giving it a bland name and an official shrug. The name is measurement. The shrug is a second rule, bolted onto the theory from outside, and the two rules together form the strangest arrangement in all of science. A masterpiece with a trapdoor in the middle of the floor. That trapdoor has a formal title, the measurement problem, and it is not a technicality. It is the crack that runs down the entire height of the second tower, from the trillion decimal scorecard all the way to the foundation. Before we can stage the collision between the towers, you need to stand at the edge of that trapdoor and look down, because the man who will eventually give us our answer spent 50 years looking down it, and what he saw at the bottom was not consciousness and not philosophy, it was gravity. Quantum mechanics, as it is actually taught and actually used, is not one law. It is two laws, stapled together, and the staple is the strangest object in physics. The first law we have met, the Schrödinger equation, smooth, deterministic, linear, letting superpositions bloom and flow, and never once collapsing them. The second law is invoked at the moment of measurement, and it says, now stop. When a measurement occurs, abandon the smooth evolution. Take the wave function, with all its overlaid possibilities, and collapse it, instantly, randomly, onto just one outcome, with probabilities given by squaring the wave's amplitudes, a recipe called the Born rule. Then, once the dust settles, resume the smooth law as if nothing happened. Understand clearly, this second rule works. The probabilities it assigns are the most accurately confirmed numbers in science. The trillion decimal scorecard from earlier is computed with exactly this recipe. But now ask the theory the obvious question, the one a child would ask. What counts as a measurement? When, exactly, does the first law hand over to the second? Does it require a detector? A photographic plate? Is a stray photon bouncing off the electron a measurement? Is a virus a measurer? A cat? And the honest answer, the answer given in so many words by the founders themselves and by every honest textbook since, is that nobody knows. The theory does not say. The most precise instrument of prediction ever devised contains, at its center, a rule that triggers on a word it declines to define. Erwin Schrödinger saw the absurdity before almost anyone, and in 1935 he sharpened it into the most famous thought experiment in the world. Seal a cat in a box with a vial of poison triggered by the decay of a single radioactive atom. The atom is a quantum object. After a while, its wave function is a superposition of decayed and not decayed. The first law is explicit about what follows. The trigger enters a superposition of tripped and untripped, the vial of broken and intact, the cat of dead and alive, not one or the other unknown to us, but both, overlaid, as legitimately as the electron in two slits. Schrödinger was not proposing this as a marvel. He was lodging a complaint. He called the situation ridiculous, and his complaint has never been answered, only managed. Somewhere between one atom and one cat, the bothness dies. The theory that predicts everything will not say where. Physicists of a practical temperament will tell you, correctly, that a real cat could never show interference, because of something called decoherence, and decoherence is real physics, worth a moment of respect. A large warm object cannot keep its superposition private. Air molecules strike it, photons scatter off it, and every collision carries away information, entangling the object's alternatives with billions of particles of environment. The delicate phase relationships that make interference visible are shredded in a fraction of a nanosecond, spread into the world beyond any hope of reassembly. Decoherence genuinely explains why we never see the stripes of bothness on anything big. But listen carefully to what it does not explain. Decoherence spreads the superposition. It does not select from it. After the air and the light have done their work, the mathematics does not say the cat is alive or dead. It says the cat plus air plus light plus planet is now one colossal superposition, more entrenched than before. The question has not been answered. It has been laundered. John Bell, the deepest thinker about these matters in the second half of the 20th century, coined a phrase for arguments like this. They work, he said, for all practical purposes, and he meant it as an indictment. A fundamental theory of nature should not need the qualifier. It is worth hearing how the language itself betrays the trouble. The word that officially triggers the second law is observation, and Penrose has a historian's complaint about it. The word crept into the foundations of physics, he says, a little too sneakily, smuggling in, under cover of a laboratory term, the suggestion that somebody must be doing the observing. Listen to how physicists actually talk, and you can hear the smuggled cargo shift around. The wave function collapses when a measurement is made. Passive voice, agent unspecified. The system is observed. By what? A photographic plate that does not observe anything in any ordinary sense. It is a slab of chemistry, made of the same atoms as the system it allegedly measures, and the smooth law claims full jurisdiction over slabs of chemistry. For a century, the second rule of quantum mechanics has been written in grammar that will not survive a single follow-up question. That is not a pedantic complaint. When a fundamental law of nature can only be stated in the passive voice, something is being hidden, and it is being hidden in the verb. The founders, to their credit, did not all hide from this. Some walked straight into the trapdoor and grabbed the most dangerous railing available. The mathematician John von Neumann traced the measurement chain link by link, particle to detector, detector to amplifier, amplifier to ink, ink to eye to brain, and observed that the smooth law, applied honestly, never breaks the chain anywhere. Every link just joins the superposition. The chain ends, he noted, only at the one place physics runs out of description, the observer's awareness. His colleague Eugene Wigner took the hint literally and proposed, for a time, that consciousness itself collapses the wave function, that mind is where the bothness comes to die. It is worth pausing on how remarkable that moment was. One of the great mathematical physicists of the century, arguing in earnest that the second law of quantum mechanics triggers on the presence of a soul, more or less. We explored that idea, and its strange afterlife, on another night. What matters tonight is the man who demolished it, because the demolition is where our story turns. Roger Penrose once had a long lunch with Wigner in Princeton and pressed him on the idea. Wigner, he reports, was gentler and less dogmatic about it than the legend suggests. But Penrose's own verdict is a small masterpiece of ridicule. Imagine, he says, a planet very much like Earth, in orbit around some far star, but lifeless. No animals, no microbes, no butterflies, no observers, and none anywhere nearby. This planet has weather. If consciousness is what collapses the wave function, then that weather, churning along for billions of years, unwatched, never becomes anything definite. Every possible storm and every possible calm coexist in one titanic superposition, waiting. Now a space probe arrives, photographs the planet, and relays the image home. The picture appears on a screen. A technician glances at it. Snap. In that instant, allegedly, an entire world's worth of weather, centuries of it, oceans of it, leaps out of limbo and becomes one history, because one primate looked at one screen. What could be more absurd? Penrose asks, and the question answers itself. Nothing rescues the idea. A planet's weather cannot be waiting on us. Whatever collapses the wave function, it is not the glance of a technician. The universe was conducting definite business for billions of years before anything opened an eye. Penrose draws the moral with characteristic bluntness. It is not consciousness that collapses the wave function. It is physics. Something physical, universal, and indifferent to observers is quietly turning maybes into facts, everywhere, all the time, and our perfect equation has no term for it. He goes further. In a single line we will leave hanging tonight. He suspects the arrow points the other way, and that whatever this collapse process is, our own awareness may depend on it, rather than cause it. That is a story we have told on another night. Tonight, we stay with the physics. Notice, before we move on, what the lifeless planet has quietly accomplished for our night's investigation. It has established the job description. Whatever the chooser is, it was at work before life existed. It is at work where no life will ever visit, and it operates with total indifference to whether its choices are witnessed. It must be cheap enough to run everywhere at once, and old enough to have been running since the first moment of the universe. Consciousness fails the description on every line. But so, when you think about it, does every force in the quantum ledger, because they are all defendants in the case. Every one of them superposes. Every one of them obeys the smooth law that creates the problem. The job description calls for something that stands outside the ledger entirely. Keep the posting pinned up. An applicant is coming. Take a breath here and feel the size of what has been said, because this is not a puzzle about electrons. This is about the room you are lying in. The lamp, the door, the glass of water, the hand at the end of your arm. All of it is made of quantum particles. And the only fundamental law we possess for those particles says that bothness is their natural condition and contains no mechanism to end it. Every solid fact around you is, in the mathematics, a suspended choice, and some verb missing from the most accurate equation ever written, is doing the choosing, in every cubic centimeter of the universe, in every instant, without pause and without credit. Physics can calculate the outcome of that choosing to 12 decimal places. It cannot name the chooser. Sit with how strange that is. The strangest fact in science is not that the quantum world is ghostly, it is that your world is not, and no one can say why. Here, at the bottom of the trapdoor, the night's question begins to sharpen. If the chooser is not consciousness, and not the environment, decoherence launders but does not choose, then it must be something in physics itself, something real, universal, always on, and yet so gentle at laboratory scales that a century of trillion decimal experiments has never tripped over it. Run through the inventory of the small world, and the candidates fail one by one. Electromagnetism, the nuclear forces, all of them are already inside the quantum ledger, already superposing, part of the problem rather than its solution. But the inventory is not empty. There is one force in nature that has never been brought inside the ledger, one force that stands apart from the entire quantum edifice, unassimilated after 100 years of effort, one force that is not, if Einstein was right, a force at all, but the shape of the stage itself. You have already guessed. Before we can accuse it, though, we have to answer a question we have been postponing since the towers went up. Just how large can the ghost of bothness actually grow? Because if there is a border where the quantum world ends, the first thing we should do is go looking for it. Science has one reliable method for interrogating a mystery, and that is to push on it until it pushes back. If superposition, the bothness at the heart of the quantum ledger, really does die somewhere between an electron and a cat, then the obvious experiment is to march up the staircase of size, step by step, putting bigger and bigger objects into two states at once, and watch for the step where nature says no. Physicists have been climbing that staircase for a century. Tonight, before we accuse anyone of anything, let us climb it together, because where the climb currently stands is one of the quietly astonishing facts of modern science. The bottom steps you already know. Electrons interfere with themselves, sent one at a time toward a pair of slits. They build up stripes, each single particle, exploring both paths and overlapping with its own alternatives. Photons do it. Neutrons do it. And neutron interferometry deserves a moment of appreciation, because a neutron is a composite object, three quarks bound together, and by the 1970s, experimenters were routinely splitting a single neutron's wave function along two paths separated by centimeters, a gap you could fit a finger through, and recombining it to find the interference intact. Whole atoms followed, then small molecules. Each step up, the ghost held. Then, in 1999, a team in Vienna did something that made textbooks around the world need new paragraphs. They took carbon-60, the buckyball, a cage of 60 carbon atoms arranged like a soccer ball, a genuinely chunky piece of matter weighing 720 atomic mass units, heated it in an oven, fired the molecules one at a time through a grating, and watched interference fringes assemble on the far side. Understand what that means. A ball of 60 atoms, a nanoscale object with an inside and an outside, hot enough to be glowing faintly in the infrared, traveled through the apparatus in a superposition of paths and interfered with itself like a beam of light. Each buckyball went through alone. Each one overlapped with its own alternative histories. The bothness was not a delicacy of electrons. It scaled. It is worth pausing on what an achievement like that costs, because the price list is itself a physics lesson. To let a hot molecule interfere with itself, the experimenters had to fight decoherence on every front at once. Vacuum chambers evacuated until a molecule could fly its whole journey without striking a single air particle. Velocities selected and paths stabilized against vibrations smaller than atoms. And even then, the buckyball's own warmth was a saboteur, because a hot molecule radiates infrared photons, and every photon it emits is a little confession of its location, a witch path record broadcast to the universe. Emit enough of them, and the interference dies, not because anyone looked, but because the information leaked. The Vienna experiments succeeded in the narrow regime where the leaks were too feeble to matter, and in doing so, they taught the modern lesson about the quantum ledger's fragility. The enemy of bothness is not size as such, and certainly not consciousness. It is information, any information, escaping anywhere. Remember that lesson. Tonight's central argument will hinge on a kind of information leak that no vacuum chamber can ever plug, because the leak is carried by space-time itself, and it kept scaling. The Vienna groups and their successors spent the next 2 decades building ever more heroic interferometers and feeding them ever more preposterous cargo. By 2019, the record stood at custom-built molecules of roughly 25,000 atomic mass units, synthetic constructions of about 2,000 atoms each, 30 sometimes heavier than the buckyball, closer in mass to a small protein than to anything you would call a particle. They interfered. In 2025, a different technique pushed further still. Nanoparticles of sodium, clusters of more than 7,000 atoms weighing around 170,000 atomic mass units, showed matter wave interference, the heaviest objects ever caught behaving as waves, each one exploring alternatives, like the electron in the double slit. To put that in a human frame, the ghost has now been demonstrated in objects roughly 1 billion times more massive than the electron where the story began. A 1 billion-fold climb up the staircase, and nature has not yet said no. The staircase has a second flight, stranger than the first, where the superposition is not of a flying object's path, but of matter standing still. Around the year 2000, experimenters working with superconducting loops, devices called squids, cooled to within a breath of absolute zero, prepared circulating currents in a superposition of flowing clockwise and flowing counterclockwise around the loop. Billions of electrons, moving in concert, in 2 opposite collective motions at once. Not some electrons one way and some the other. The entire current, both ways, in the full quantum sense. A macroscopic electrical event refusing to choose its direction. And in 2010, a team in California achieved what many consider the most unsettling rung yet. They took a tiny mechanical resonator, a sliver of solid material, big enough to see with the naked eye if you squinted at its holder, containing on the order of 1 trillion atoms, cooled it until its vibration reached the quantum ground state, and then coaxed it, briefly, into a superposition of vibrating and not vibrating, a manufactured object, a thing with a serial number in effect. For a few tens of nanoseconds, it moved and did not move, in the same sense that Schrödinger's atom decayed and did not. The press called it the first quantum machine. The staircase had reached the world of engineered, touchable things, and the ghost was still climbing. Now pause on the pattern, because the pattern is the point. A century of climbing, a billion-fold increase in mass, superpositions of paths, of currents, of vibration, of matter hot and cold, flying and standing still, and not once, at any step, has anyone caught the bothness failing of its own accord. Wherever experimenters have managed to shield the fragile phase relationships from the shredding of the environment, and that shielding is the whole heartbreaking art of these experiments, the vacuums and the cold and the isolation. The superposition has been there, intact, exactly as the flat ledger demands. Decoherence explains every failure we have ever had. It is the noise, the practical enemy. But beneath the noise, no border, no step where the staircase ends. If you extrapolate the record with a straight edge, the conclusion writes itself. Superposition goes all the way up. Cats, beads, planets, weather. The many worlds reading of quantum mechanics, which we have visited before on this channel, takes exactly that straight edge seriously. The ledger never collapses, and every alternative persists in a perpetually branching totality. That is one honest response to the staircase. Keep it on the table. Tonight's guest will offer another. But before we leave the staircase, notice something about every experiment on it. Something so obvious, it took decades for its significance to surface. Every object on the climb, from the electron to the trillion-atom resonator, is tiny. Not tiny in atom count, we have just celebrated the atom counts, but tiny in the one currency that will matter for the rest of the night. Mass, and the gravitational presence that mass brings. A 25,000-unit molecule is a giant of the quantum world and a nothing of the gravitational one. Its own gravity is so faint that no instrument on Earth could detect it. A distortion of space-time, somewhere down past the 20th decimal place. The staircase, for all its billion-fold glory, has been climbed entirely within the one regime where the two towers never have to speak, where the curvature of Einstein's world is so utterly negligible that the flat ledger of the quantum world proceeds as if geometry did not exist. Every rung, without exception, sits in the shallow end. Run the comparison as numbers, because the numbers are the argument. The gravitational pull between two of the record-holding molecules, set side by side, is weaker than the electromagnetic forces in the apparatus by something like 30 powers of 10, a disparity so complete that including gravity in the calculation would be like adjusting the weight of a container ship for the breath of a moth. Physicists do not neglect gravity in these experiments out of carelessness. They neglect it because arithmetic laughs at them for considering it. And that, precisely, is the blind spot. Every triumph on the staircase certifies that superposition survives where gravity is arithmetic's joke. About the regime where gravity has a voice, where an object's mass is enough to bend the stage it stands on. The entire century-long record says exactly nothing. The most confirmed principle in physics has been confirmed, without exception, in the one arena where its deepest rival was not present to object. So the record deserves a more careful sentence than the triumphant one. It is not that nature has never said no to a large superposition. It is that we have never yet asked the question loudly enough for the one silent party to hear it. There is a force that has sat out every experiment on the staircase, too weak to register on any rung we have reached. And yet, if the first tower is right, not a force at all but the shape of the arena every experiment stands in. Nobody has ever placed an object in superposition whose gravity mattered. Nobody has ever made space-time itself hold two shapes at once and checked whether the universe permits the arrangement. That experiment, the loud version of the question, has never been run. And here is the thought to carry into the next part of the night, the thought that reframes the entire staircase. Perhaps the border we failed to find was never a horizontal line at some magic size. Perhaps it is drawn in the one ink none of our experiments has yet touched. To see why anyone would think so, we must now do what physics spent 70 years trying to do, and watch it fail. We must try to force the two towers into a single building. Physics does have an official plan for ending the standoff between the towers, and the plan is now old enough to draw a pension. The plan is called quantum gravity, and its guiding assumption has been the same since the 1930s. Quantum mechanics is the deeper framework, and gravity must be brought inside it. In Roger Penrose's dry phrasing, the program is to haul general relativity into the framework of quantum theory, to do to Einstein's geometry what was done, with spectacular success, to electricity and magnetism. That earlier conquest produced quantum electrodynamics and the trillion decimal scorecard. The same recipe, applied to the other forces of the nuclear world, produced the rest of the standard model of particle physics. 3 of nature's 4 fundamental interactions have been hauled inside the ledger, each resisting for a while, and each eventually yielding. Gravity is the 4th. It has been resisting for 90 years. The trouble announces itself the moment you try. Follow the recipe. The gravitational field, like the electromagnetic field, should come in quanta. Particles called gravitons. Ripples of space-time, as photons are ripples of the electromagnetic field. So far so good. Nothing forbids the graviton, and if gravitational waves exist, which we now know directly, then their quanta presumably exist too. But when you push the recipe further and ask it to compute, to give you numbers for gravitons scattering off gravitons, the bread-and-butter calculations that made quantum electrodynamics famous, the machinery breaks. The calculations return infinities. Infinities appeared in the other theories too, but there they could be tamed by a disciplined bookkeeping procedure called renormalization, absorbing the infinite quantities into a few measured constants. Gravity refuses the discipline, because gravity couples to energy, and gravitons themselves carry energy. Gravity gravitates. The feedback loop we met when we built the first tower, and the infinities breed faster than the bookkeeping can absorb them. New species of infinity appear at every level of approximation, each demanding its own new constant, until the theory needs infinitely many measured inputs and predicts nothing at all. By 1986, a careful calculation had settled the matter beyond appeal. Einstein's theory, treated by the standard quantum recipe, is what physicists call non-renormalizable. The recipe that conquered 3 forces does not merely struggle with the 4th. It fails, structurally, for reasons woven into what gravity is. Worse, nature has hidden the answers far beyond our reach. Every force has a natural scale where its quantum character becomes unmissable, and for gravity, that scale, the Planck scale, sits at energies around 10 to the 19th power billion electron volts, and lengths around 10 to the minus 35th power meters. Our most powerful particle accelerator reaches energies roughly a quadrillion times too small. To probe the Planck length by the usual method of smashing things harder, you would need an accelerator not the size of a city, but roughly the size of a galaxy. And even that undersells the wall, because of a beautiful trap. Probing smaller distances requires concentrating more energy into less space, and concentrate enough energy to resolve the Planck length, and you create a black hole, which swallows the very information you were trying to extract. The universe, with what can feel like deliberate mischief, has locked the room where the towers meet and posted a horizon at the door. And beneath the technical failures lies a conceptual one that may be the deepest of all, though it can be stated in a single breath. Quantum mechanics needs a clock. The Schrödinger equation describes how the wave function changes in time. Time is the fixed external metronome against which all the maybes evolve. But in general relativity, time is not a metronome outside the world. It is part of the geometry, stretched by mass, sliced differently by every observer, one of the performers on stage. Try to write a quantum equation for the whole universe, where the geometry itself is the quantum system and the metronome disappears into the orchestra. The resulting equation, infamously, has no time in it at all. Physicists have wrestled with that embarrassment. It is called the problem of time, for over half a century, and we have brushed against it on other nights. The point for tonight is simple. The marriage of the towers does not founder on technique alone. The two theories disagree about what time is, which is not the kind of disagreement a clever approximation can paper over. None of this has stopped the program. Physicists are not easily discouraged, and the quantum gravity effort has produced towering mathematical structures, decades of them, including one famous framework, whose own internal crisis we have examined on another night here, and rival approaches that dissolve spacetime into loops and networks. What matters for tonight is the honest scoreboard. After 90 years, no quantized theory of gravity has produced a single confirmed prediction. Not one experiment, anywhere, has ever measured a quantum gravitational effect. The program may yet succeed, but it is fair, it is overdue, to ask a question that sounds almost impolite. What if the program has the direction of conquest backwards? Let us step back, here at the midpoint of our night, and restack everything we have built, because the pieces are now all on the table and the shape they make is worth seeing whole. We built the first tower. Gravity is not a force but geometry, founded on the principle of equivalence, fall, and gravity vanishes, like the sphere of sparks. We built the second. Matter is a flat ledger of overlaid possibilities, founded on the principle of superposition, confirmed to a trillionth, and containing a trapdoor, a missing verb, with no rule for how possibilities become facts. We searched for the border where the ledger fails, climbed a billion-fold staircase of ever larger superpositions, and found no border, but noticed that every rung was gravitationally silent. Every experiment played out in the shallow end, where geometry never speaks. And we have now watched the official plan for unification. Quantize gravity, haul the geometry into the ledger, fail structurally for 90 years, its answers locked behind a wall of energy no civilization could scale. Two perfect theories, one missing verb, one force that won't fit, and one region of the map, massive objects in superposition, where no experiment has ever gone. Hold all of that at once, and a suspicion begins to form, quietly, the way a face emerges from a puzzle you have stared at too long. Physics has spent 90 years assuming that in the marriage of the towers, quantum mechanics is the senior partner, that its rules are the true constitution, and geometry must be redrafted to comply. This assumption was never argued. It was inherited from the habit of victory. The recipe had won 3 times, so it would win a 4th. But look where the failures actually sit. The quantum recipe fails on gravity. Gravity's answers are hidden beyond reach. And meanwhile, in the other tower, quantum mechanics is the theory walking around with a hole in its own foundation. The measurement problem, the undefined trigger, the chooser it cannot name. One of our theories is internally complete and externally untested at the join. The other is externally flawless and internally broken. If you met these two theories as witnesses in a courtroom, which testimony would you trust about the join? History, as it happens, has seen this exact posture before, and the precedent is instructive. At the end of the 19th century, Physics possessed two magnificent frameworks, Newton's mechanics and Maxwell's electromagnetism, and they, too, contradicted each other at the root, over the question of whether the speed of light could depend on the observer. The consensus assumed the older, more established framework would absorb the younger. Mechanics was the constitution, and light would be made to comply, propagating through some mechanical medium that experiments duly went hunting for. The hunt failed, decade after decade, until a patent clerk suggested the unthinkable, that the junior theory's strange principle was the true one, and the senior framework, mechanics itself, was the approximation that had to yield. The result was relativity, and the lesson was not that Newton was foolish, but that seniority is not evidence. When two great theories collide, the one that must break is not necessarily the older, nor the stranger, nor the one with fewer decimal places on its scorecard. It is the one whose foundational principle turns out to be the imposter, and history offers no shortcut for telling which that is in advance. So permit the impolite thought its full voice. Perhaps gravity is not the junior partner awaiting quantization. Perhaps the influence runs the other way. Perhaps it is gravity, the shape of the stage, that disciplines the quantum ledger, and the missing verb has been gravitational all along. Notice how neatly the suspicion fits the facts we have stacked. The chooser must be universal. Gravity couples to everything, without exception. The chooser must be indifferent to observers. Geometry does not care who is looking. The chooser must be utterly negligible for electrons and atoms and even trillion atom slivers. And gravity, at those masses, is negligible almost beyond expression, weaker than the other forces by dozens of powers of 10. And the chooser must grow ruthless somewhere on the road to cats and chairs and planets. And mass is exactly the currency that grows along that road. Every property the missing verb requires, gravity has. That is not a proof. It is a scent. But it is the scent that one particular physicist has been following, almost alone, for half a century. It is time to meet him properly. He is in his mid-90s now. He shared the Nobel Prize in Physics in 2020 for proving, back in the 1960s, that black holes form inevitably under Einstein's equations. Work done jointly, in part, with Stephen Hawking. He has spent a lifetime inside general relativity, which may explain why he never absorbed the reflex that geometry must kneel to the ledger. And he believes he can show you, with no accelerator, no black hole, no Planck scale anything, just a tabletop, the Earth's gentle field, and one small object asked to be in two places, that the two towers do not merely fail to communicate. They contradict each other, here, now, in the room where you are lying. His argument is the heart of tonight, and it begins with the most innocent question imaginable. How do you describe a laboratory that is standing still? Roger Penrose's argument begins with a situation so ordinary that no working physicist would give it a second glance. A quantum experiment, sitting on a table, in a laboratory, on the Earth. Some small quantum system is doing whatever quantum systems do. An atom in a trap, a particle in flight, and, because the laboratory is on a planet, the Earth's gravitational field is present in the room. Feeble, familiar, unremarkable. The question Penrose asks is the one nobody bothers to ask. How, exactly, should we include that gravity in our quantum description? And the trap, the deep, patient trap that took him decades to fully appreciate, is that the two towers each volunteer an answer. The answers look almost identical, and they are not. The first answer is the practical one, the one in every textbook, and it belongs in spirit to Newton. Treat gravity as a force, or more precisely, as an energy. Every position in the room has a gravitational potential energy, higher near the ceiling, lower near the floor, and you simply add that energy into the quantum bookkeeping, into the object called the Hamiltonian, the theory's master ledger of energies that drives the Schrödinger equation. This is what any sensible physicist does, and it works beautifully. Neutrons dropped through rising beams bend their interference patterns by exactly the predicted amount. Quantum particles bounce on mirrors in Earth's field, in quantized heights. Every measurement ever made in a terrestrial laboratory is consistent with this recipe. Gravity, in this telling, is just one more energy term in the flat quantum ledger. Nothing special. Next entry. But now Einstein clears his throat from the corner of the room. Penrose likes to imagine him, or Galileo, sitting there, politely objecting. That is not what gravity is, says the first tower. Gravity is not an energy painted onto the room. Gravity is the room falling. If you want the honest description, take the perspective in which gravity vanishes, the freely falling frame, the frame of the sphere of sparks. In those coordinates there is no gravitational term at all. There is simply a laboratory accelerating upward through a gravity-free world, its floor pressing up against everything in it, which is, after all, exactly what your legs report when you stand. Describe the quantum system that way, says Einstein, in the coordinates where the field is erased, and you will be describing what is actually happening. Neither answer, let it be said clearly, is a straw man. The Newtonian recipe is not a lazy approximation. It is the working language of every quantum laboratory on this planet, and it has been tested against gravity directly. In a classic experiment first performed in 1975, physicists sent neutrons around an interferometer loop tilted in the Earth's field so that one path ran higher through slightly weaker gravitational potential than the other. The two paths' wave functions accumulated different phases, and when recombined, the interference stripes shifted by precisely the amount the potential term in the ledger predicted. Gravity, that experiment showed, does reach inside the quantum ledger and move the entries around, exactly as the practical recipe says. And the Einsteinian answer carries the authority of the entire first tower, of every eclipse, every clock correction, every gravitational wave. Two answers, each certified by decades of experiment, each entitled to the room. That is what makes what follows a trap rather than a quibble. Here is the marvel. You can do the calculation both ways, and quantum mechanics permits both. The Newtonian version, with its potential term in the ledger, the Einsteinian version, with no gravity and an accelerating room. Two descriptions of one experiment, one from each tower, and when you compare the two wave functions, they agree, almost. They give identical predictions for every position, every interference stripe, everything a detector in the room could register. The difference between them is confined to a single mathematical appendage, a phase factor, a kind of internal clock hand angle that multiplies the whole wave function. Phases that multiply everything are normally the definition of harmless. They cancel out of every observable quantity, which is precisely why generations of physicists have computed this comparison, shrugged, and moved on. Almost identical. The word almost is carrying more weight than any word in physics. Because look closer at that phase, as Penrose did. It is not a constant angle, and not even an angle turning at a steady rate. The exponent contains the time multiplied by itself 3 times, time cubed. A phase spinning ever faster, its disagreement between the two descriptions compounding as t times t times t. And in quantum field theory, the deeper, more honest version of quantum mechanics, the one that describes particles as excitations of underlying fields. A runaway phase of that kind is not harmless at all. It is a symptom with a diagnosis. It signals that the two descriptions are built on different vacua. The vacuum in quantum field theory is not simply nothingness, it is the reference state of the world, the definition of what counts as empty, and, critically, of what counts as a particle. Two descriptions with genuinely different vacua are not two photographs of one scene from different angles. They are two different accountings of reality that cannot be laid on top of one another. Choose the Newtonian description, and the Einsteinian one is not just rotated relative to yours, it disagrees with you, at a compounding rate, about the meaning of empty space itself. The towers have not merely offered different conventions. Each is quietly insisting on its own definition of nothing. If the phrase different definitions of empty sounds like mysticism, Anchor it in something physicists have known since the 1970s. The vacuum of quantum field theory is observer-relative in ways that still astonish. The most famous result of this kind says that an accelerating detector, moving through what an inertial observer swears is perfect emptiness, will register a faint warmth, a bath of particles conjured, from the accelerating perspective, out of the same nothing. Emptiness, in other words, is not a fact about the world alone, it is a fact about the world and the motion of whoever is asking. Penrose's tabletop comparison drives that unsettling relativity home at the gentlest possible scale. His two accountants, one hovering with Newton, one falling with Einstein, are in relative acceleration, and so they inherit exactly this quarrel about what empty means, growing at time cubed. The quarrel was always latent in the physics. The superposed bead, in the next part of our story, is what forces it into the open. Now, is this yet a catastrophe? Penrose is scrupulously honest here. Not quite. For this one experiment, one laboratory, one uniform field, one description chosen and used consistently, you can, as he puts it, stick to your vacuum and get the right answers. Pick Newton's ledger and never look at Einstein's, and no detector will betray you. The crack does not yet leak, but feel what has already happened, because it is the quiet turning point of the entire night. We asked the two most successful theories in the history of science to co-describe the gentlest possible situation, not a black hole, not the first instant of creation, but a room, standing still, on an ordinary planet, and their answers disagreed about the nature of emptiness, with a disagreement that grows as time cubed. Every deeper contradiction we meet from here on is this one, amplified. The fault line does not run through exotic territory, it runs through the floor of every laboratory on Earth, and it has been papered over, brilliantly and successfully, by the practical habit of never asking both towers at once. Let me put you inside it, because this is one of those places where the physics deserves to be felt rather than described. You are sealed inside a windowless laboratory, a comfortable room with benches and instruments and a pen lying on the desk. You cannot see out, and the room is very quiet. You reach for the pen and it is floating, drifting a hand's width above the desk, turning slowly, going nowhere. Your own body has gone weightless in the chair. Around you the instruments hang serene in the air, a constellation of small objects at rest among themselves. And you realize, with a slow smile in the dark, where you have been all along, inside the sphere of sparks. Your room is one of Galileo's embers, falling freely through some field you cannot feel, and by the oldest mercy in physics the fall has erased gravity from your world completely. Inside these walls there simply is no such thing as down. Now, gently, the room is set on the ground. Weight returns like a tide. The pen settles to the desk. Your body sinks into the chair. The floor resumes its patient push against everything above it. Nothing about the room has changed but its circumstances, and yet two honest accountants now file two different reports of it. One writes, "A gravitational field fills this room, and every energy in it pays the field its due." The other writes, "There is no field. This room is simply accelerating, floor first, through emptiness." Both reports predict every reading on every instrument on the benches, and in a hidden column, in ink no instrument can see, their versions of emptiness itself are spinning apart, faster and faster, as time multiplied by time multiplied by time. Hold that unease, and hold one more fact. Everything so far assumed the Earth's field was the only gravity in the story. One field, one fall, one sphere of sparks to hide inside. The quantum system on the bench was a lightweight, a ghost with no gravitational voice of its own. Penrose's masterstroke, the step that converts a philosophical itch into a collision with consequences, is to revoke that assumption. Give the quantum system a body. Let the thing on the table have mass enough that its own gravity, however small, is part of the story, and then ask it to do the one thing quantum objects do best. Ask it to be in two places at once. The moment we do, the paper over the crack tears, because the oldest mercy in physics is about to fail for the first time. The object at the center of the collision could not be humbler. Penrose asks us to imagine a small lump of matter. He variously calls it a bead, a little stone, a speck, sitting in the laboratory we have just left. It is not exotic. It is a grain of ordinary stuff, large enough that its own gravitational field, while absurdly faint, is real. A genuine dimple in the geometry of the room, the same kind of dimple the Earth makes, scaled down by a factor with dozens of zeros. Every object you have ever touched makes such a dimple. You make one yourself, so does your pillow. Gravity is universal. That was the first tower's opening claim. And universal means the bead is not exempt. Where the bead sits, space-time bends minutely around it. Now perform the standard quantum ritual. Using techniques that are bread and butter on the billion-fold staircase, place the bead into a superposition of two locations, here and there, separated by some small distance. The second tower not only permits this, it insists the arrangement is routine, just one more entry in the flat ledger, the same bothness we have verified in electrons and buckyballs and trillion-atom slivers. Fine. But attend now to what the superposition drags with it. The bead is a gravitating body. Its dimple in spacetime goes where it goes. So if the bead is in a superposition of here and there, then its gravitational field, the local shape of space and time, is in a superposition of two configurations. Dimple on the left, dimple on the right. We have not superposed a mere particle. We have superposed the geometry of the room. For the first time on the staircase, the stage itself has been asked to hold two shapes at once. And at this exact point, the two load-bearing principles of physics grab the same object and pull in opposite directions. Watch the equivalence principle try to do its work. Its guarantee, remember, is that gravity can always be locally erased. Fall freely, join the sphere of sparks, and the field vanishes from your world. But fall with which field? Suppose you free fall into step with the left-hand dimple. You have erased the left branch's gravity, and the right branch's field remains in your world, unerased, tugging. Free fall instead with the right-hand dimple, and the left branch's gravity survives. Penrose states the predicament with disarming simplicity. As I get close to the bead, whether it is here or here, I cannot get rid of them both at once. There is no motion, no frame, no falling laboratory, none, in which both branches' gravity is simultaneously erased. The oldest mercy in physics has failed. Galileo's trick, the trick that worked for every spark in the sphere, for every astronaut, for every falling apple in 4 centuries of physics, does not work on this bead, because the bead's bothness has given the world 2 downs, and a faller can only fall down one of them. Stand on the tabletop beside it, if you will, for a moment, shrunk to its scale, in the quiet of the laboratory night. In front of you, the bead rests here, a grey fleck on the white surface, and also there, a hair's width away. Not a copy, not a twin, but the same single grain, unwilling to have chosen. Beneath each of it, invisible but real, space-time sags into its private dimple, 2 shallow basins in the fabric of the room, and you decide to do the oldest thing in physics. You decide to fall. You lean into the left basin's pull, give yourself to it, and for a heartbeat the mercy comes. Weight lifts. The left dimple's gravity dissolves around you. You are a spark in its sphere. But across the small dark of the tabletop, the right basin still holds its shape, still pulls, unerased, real as a moon. So you catch yourself and fall the other way instead, and it happens again in mirror image. The right dimple forgives you, and the left one does not. Back and forth, and it is never both. 400 years of falling has always bought freedom. Tonight, for the first time, the purchase fails. Under your feet there are 2 floors, 2 geometries, 2 versions of straight, two rates at which time itself intends to pass. The room has become a chord where the world has only ever played single notes, and something, somewhere, in the structure of law, is being asked to yield. It is worth asking why nobody noticed this collision for the better part of a century, because the answer absolves no one and explains everything. The collision requires both towers to be present at full strength on the same object at the same moment, and physics, as a profession, is organized to prevent exactly that. The people who spend their lives inside the quantum ledger work with electrons and photons and atoms, objects whose gravity is arithmetic's joke. For them, Einstein's corrections are a rumor from another department. The people who spend their lives inside the geometry work with stars and black holes and the universe entire, objects whose quantum fuzziness is unmeasurable in principle with any instrument they will ever own. For them, superposition is a rumor from the other direction. Each culture learned, correctly, that it could ignore the other's tower without ever being punished by an experiment, and an unpunished habit hardens into an unexamined truth. The superposed bead lives in the no man's land between the departments, too heavy for the quantum culture's instincts, too ghostly for the gravitational culture's, claimed by neither, assigned as homework by both to the other. Penrose's peculiar advantage was that he never fully belonged to either culture. A geometer by training who took the quantum ledger's foundations personally, and no man's land is where he chose to live. Let us be precise about what is yielding, because the trouble is deeper than a failed maneuver. The mathematics of the second tower, the flat ledger, is built on adding possibilities, state 1 plus state 2, in fixed proportions, evolving smoothly on a common stage. But when the two states are two spacetimes, the addition itself loses its meaning. To add the wave function's value at a given point across the two branches, you must say which point in the left geometry corresponds to which point in the right, and there is no lawful answer. The two geometries carve the room differently, and no principle of either tower matches them up. Even the instants disagree. Time near a dimple runs minutely slower, so the two branches do not even share a common ticking against which to be added. Superposition needs a stage, and general relativity has made the stage itself a performer. The ledger's central operation, the plus sign that has never failed, arrives at the bead and finds no table to write on. I promised you at the start of the night that the contradiction between the towers was not confined to black holes and the birth of the universe. And here it is, redeemed in full. No horizon, no singularity, no Planck-scale energies. A grain of matter, a table, the gentlest field in nature, and the two most successful theories our species has produced, issuing instructions that cannot both be followed. The principle of superposition says, the bead's bothness is lawful, keep the ledger flat, add the states. The principle of equivalence says, gravity is geometry, and geometry is erasable by falling, and it cannot erase this. Physics' two best theories contradict each other, not in some distant regime, but here, at the mass of a speck, at arm's length from where you are lying, and one of them has to break. Which one? The geometry or the ledger? We still cannot say. The collision alone does not name the loser. But notice what the collision has already accomplished. It has drawn, at long last, the border we searched the staircase for, and never found. The border of the quantum world is not a size, not an atom count, not a temperature. It is the point at which an object's bothness starts to tear the stage. The point where superposition and space-time can no longer pretend the other is not there. And notice one more feature of the border, the one that will turn out to be its signature. It is not a wall, but a gradient. The bead's two dimples do not either tear the stage or leave it whole. They tear it by an amount that depends on how much mass is superposed and how far apart the branches sit. Make the bead lighter, and the two geometries crowd so close to identical that the stage's tearing shrinks toward nothing. The ledger's plus sign finds, in effect, a a table to write on after all, and the bothness can persist in peace. Make the bead heavier, and the geometries diverge, the mismatch grows, and whatever strain the arrangement puts on the laws of physics grows with it. The contradiction, in other words, comes in degrees, and anything that comes in degrees can, at least in principle, be quantified. That is the thought that separates Penrose from a century of hand-wringing about measurement. Where others saw a paradox to be interpreted, he saw a quantity to be calculated. How much, exactly, does a given superposition tear the stage? Put a number on the tear, and you might put a number on its consequences. Faced with a contradiction this clean, there are two honourable responses. A mathematician would demand the new, deeper theory in full before saying another word, and no one on earth, Penrose included, possesses it. A physicist does something humbler and more cunning. Penrose's own words, delivered with the smile of a man confessing a professional secret. I do what any sensible physicist would do. I cheat. The cheat is this. Keep using the flawed Newtonian description, the ledger with its gravity term, the one we know is not honest about what gravity is. But track the size of the error you are committing by using it. Do not resolve the contradiction, measure it. Ask, how badly, in units an experimenter could care about, do the two irreconcilable descriptions of the superposed bead actually differ? It sounds like bookkeeping. It is bookkeeping. And out of that bookkeeping is about to fall a number, a lifetime, in seconds, that may be the first quantitative crack ever found in the perfect second tower, and the answer to why your world has never once looked like both. The cheat proceeds in 3 moves, and you can follow every one of them. Penrose keeps the Newtonian description of the superposed bead, the dishonest one, the one that paints gravity into the ledger as a mere energy and pretends the stage is intact, and he asks, at each point in space, how large is the error I am committing? The error lives in the disagreement between the two branches' gravity. At every location in the room, the left-hand bead's field pulls one way, and the right-hand bead's field pulls slightly differently. The mismatch between those two pulls, point by point, is the precise measure of how badly the single flat stage is failing to represent two geometries. First move, write down that mismatch everywhere. Second move, add it up. Integrate the disagreement over all of space, gathering every point's small failure into one total. Third move, and Penrose describes this with the fondness of a craftsman recalling a good afternoon. A little integration by parts, a standard algebraic massage, and some fiddling around, and the total rearranges itself into a quantity physicists have known for 2 centuries, an energy. Specifically, it becomes the gravitational self-energy of the difference between the two mass distributions. In plain terms, the energy it would cost, counting gravity alone, to pull one copy of the bead away from the other, from overlapping to separated. Call it E sub g. It is a perfectly definite number. For any real bead, it is almost comically small. For a grain of dust, in a superposition, spanning its own width, E sub g works out to something like a billionth of the energy in a single flea's jump. That is the entire size of the contradiction between the towers, expressed in energy, the price of the torn stage. A cynic would stop here and laugh. An energy that small has never mattered to anything. But Penrose's next step is the one that turns a bookkeeping note into a prediction, and it runs through the most reliable exchange rate in quantum mechanics. Notice what kind of quantity the error is. It is an irreducible ambiguity in the energy of the superposed state. The two branches cannot agree on the gravitational books, so the state as a whole does not possess one sharp energy. Its energy is fuzzy, uncertain, by an amount E sub g. And quantum mechanics has known for a century what an energy uncertainty means. It is not an inconvenience. It is a lifetime. Here is the exchange rate at work in a place you have already met it. Particle physicists deal constantly in unstable particles, resonances that exist briefly and decay. When they measure such a particle's mass repeatedly, they never get one value. They get a smear, a fuzziness in the mass itself. And the fuzziness obeys a beautiful law, a direct consequence of Heisenberg's time-energy uncertainty relation. The width of the smear, multiplied by the particle's lifetime, equals Planck's constant, near enough. Sharp mass, long life. Fuzzy mass, short life. The relation runs both ways and has been confirmed in thousands of measured particles. It is how short-lived particles' lifetimes are actually determined. Nobody times them with a stopwatch. They read the lifetime off the fuzziness of the mass. An uncertainty in energy is a countdown clock. That is not an analogy. In quantum mechanics, it is an identity. Now put the two halves together, exactly as Penrose did in the mid-1990s. The superposed bead is a state whose energy is irreducibly uncertain by the amount E sub g, the gravitational disagreement between its branches. Treat it, therefore, as what the mathematics says it is, an unstable state, a resonance, with a lifetime given by the same exchange rate that governs every decaying particle. Lifetime equals Planck's constant divided by E sub g. Write it small. Tau, approximately, equals h bar over E sub g. That is the entire formula. A superposition of mass distributions is not a permanent resident of reality, as the flat ledger claimed. It is a decaying particle whose decay product is definiteness. It lives, on average, for a time set by gravity's quarrel with it, and then it collapses, physically and spontaneously, into one branch or the other. No observer required, no consciousness, no detector, no undefined trigger word. The missing verb of quantum mechanics, in this proposal, has been found, and it was written in Einstein's ink. Gravity is the chooser, and the fuzzier a superposition makes the geometry, the shorter the bothness is permitted to live. Feel how strange and how domestic the mechanism is. Nothing reaches in from outside to strike the superposition down. No observer, no detector, no cosmic sensor. The state simply cannot hold its own books. Its two branches disagree about the gravitational accounts by E sub g. The disagreement is an energy fuzziness, and an energy fuzziness, by the plainest law in the quantum canon, is mortality. The superposition dies of an internal inconsistency, the way a government falls when its ministries cannot agree on the budget, and the choice of survivor, when the collapse comes, is random, weighted by the ledger's own probabilities. Chance enters exactly where the old theory smuggled it in through the measurement rule, but now attached to a physical process, with a physical schedule, rather than to an undefined word. Before we test this formula against the world, pay it the compliment of noticing how little it asks of us. Proposals to modify quantum mechanics have circulated for decades. Respectable ones, which add new random collapse processes to the Schrödinger equation. But they come with dials, new constants of nature, collapse rates and length scales, adjustable numbers that must be tuned to hide the new physics from every experiment so far. Penrose's formula has no dials. Both ingredients, the gravitational self-energy and Planck's constant, were already on the books. Gravity itself sets the scale of its own intervention, and there is a second author on the ledger, which in science is a mark of credit rather than embarrassment. Years before Penrose's argument, in 1987, the Hungarian physicist Lajos Diósi, working in Budapest along an entirely different route, arrived at the same expression, the same self-energy, the same lifetime. Penrose learned of it afterward and has been scrupulous about the shared credit ever since. The proposal is properly called the Diósi-Penrose model. Two physicists, 2 decades apart in inspiration, 2 unrelated derivations, 1 formula. When independent roads meet at the same address, it is reasonable to suspect somebody lives there. Now the test. And this is the moment the whole night has been building toward, so take it slowly. A formula that kills superpositions, had better kill the right ones. It must spare every ghost on the billion-fold staircase, because we have seen them, and it must execute the cat, the chair, and the planet's weather without measurable delay, because we have never seen them fail to be definite. Run the numbers. For an electron in a superposition, E sub g is so fantastically small, gravity caring so little about so little mass, that the lifetime tau stretches beyond the age of the universe, not by a factor of 10 or 1,000, but by an amount that beggars description. The electron's bothness, on this theory, will essentially never collapse of its own accord, which is precisely what a century of flawless interference experiments requires. The buckyballs, the 25,000-unit molecules, the sodium nanoparticles, even the trillion-atom sliver, all of their lifetimes come out ludicrously long compared to any laboratory timescale. The formula stands aside and lets them interfere, exactly as observed. Every rung of the staircase survives. But now climb where no experiment has yet climbed. Penrose has published the illustrative benchmarks: a droplet of water, a fraction of a micron across, a speck at the edge of visibility under a good microscope, held in a superposition of two locations, collapses in a matter of hours. Make the droplet 10 times wider, and the lifetime plunges to a 20th of a second. 10 times wider again, now a barely visible fleck, and the bothness survives for about a millionth of a second. And anything at the scale of everyday life, the dust mote drifting through your lamplight, in Penrose's phrase a mere flick of dust, collapses so fast that no process in physics could ever catch it being in two places. A cat's lifetime as a superposition would be so far below any meaningful instant that writing the number would be a typographical stunt. The formula draws the border of the quantum world, and the border falls exactly where our universe has always put it. Everything on the staircase ghostly, everything in your bedroom solid, and a thin, precise, testable frontier in between, in the country of the specks. Stay here one more moment, because something has just happened that has never happened before in this story, and it deserves to be felt. For 100 years, the solidity of the everyday world has been an assumption physics worked around. The one fact, too obvious to derive. Every interpretation either postponed the question, or multiplied worlds to dissolve it, or gestured at observers. Tonight, for the first time, you have watched a formula derive it. The chair holds one shape. The door is only open or closed. Your hand is exactly where you left it. Not because someone is watching, not because large things are forbidden their ghosts by decree, but because everything with real mass is paying gravity's tax on ambiguity, continuously, at a rate that makes definiteness instantaneous for furniture and eternal business for electrons. The difference between the ghost world and the solid world was never consciousness, and never magic. On this proposal it is arithmetic. H bar divided by a gravitational disagreement, running silently in every cubic centimeter of the universe, in the walls of your room, in the planet under your bed, in you, since the beginning of time. The world is definite, if Penrose is right, because the world is heavy. But a physical collapse, unlike an interpretive shrug, must answer physical questions, and one of them is waiting with its arms crossed. Collapse happens, we now say, after a lifetime tau. Happens where? Happens when? The bead's branches may be separated by a hair's width, but nothing in the formula forbids superpositions whose branches drift meters apart, or kilometers, before the clock runs out. When the choice finally comes, it must come to both branches, coordinated, total, leaving exactly one survivor. And the first tower, Einstein's own, contains a commandment we have not yet reckoned with tonight. No influence, no coordination, no agreement of any kind may travel faster than light. An instantaneous collapse across a separation sounds like precisely such an influence, which raises the delicious possibility that Penrose's cure for quantum mechanics violates the very relativity it was built to honor. And his answer to that charge is, by his own cheerful admission, the craziest thing he believes. Special relativity is not merely a theory of fast objects, it is a constitution for the universe, and its first article is a prohibition. No signal, no influence, no coordination of events may travel faster than light, not because light is precious, but because in Einstein's spacetime, faster than light influence is time travel in disguise. Observers moving at different speeds slice spacetime into different sequences of now. We spent an evening on another night walking through why there is no universal present moment. The consequence is brutal for any theory that wants things to happen instantaneously across a distance. Instantaneous in whose slicing? An influence that leaps across space in one observer's now is, for another equally valid observer, arriving before it departed. Permit such influences to carry messages, and you permit answers to precede questions, effects to lobby their own causes. The Constitution does not bend on this point, and a physical, objective collapse of the wave function, a real event, happening to a real spread-out state, all at once, looks, on its face, like a flagrant violation drafted in broad daylight. Sharpen the problem with the scenario that has haunted quantum mechanics since 1935. A single quantum system splits into two correlated partners. The arrangement Einstein, Podolsky, and Rosen made famous. And the arrangement we have met before on this channel in the language of entanglement. Prepare two particles whose spins are perfectly anti-correlated. Measure both along the same axis, and if one says up, the other must say down, without exception. Now send them apart. Across the laboratory, across the city, across a galaxy if you like. Distance changes nothing in the mathematics. Alice, on her side, measures her particle. The joint wave function, one object spanning both locations, collapses. Her particle commits to up, and in the same stroke, the distant partner commits to down. Bob, arriving at his particle a moment later, will find the commitment already made. Something, it seems, has happened at Bob's location because of an event at Alice's, with no time allowed for light to carry the news. Experiments have verified these correlations to exhaustion. The 2022 Nobel Prize honored the physicists who nailed the question shut. The correlations are real, and if collapse is a physical process, as Penrose insists it must be, then the process looks instantaneous across arbitrary distance, and the Constitution's first article looks broken. Make the scenario concrete enough to lie awake with. Put Alice on a ship bound outward past Neptune, and Bob in a laboratory on Earth, each carrying one particle of the pair in a magnetic bottle. 4 hours of light travel time separate them. Alice, at some appointed moment, measures her particle along the vertical axis and gets up. If collapse is a real physical event, then at that moment, whatever that moment even means across 4 light hours, the joint state of the pair ceases to be a superposition, and Bob's particle, in its bottle on Earth, is henceforth simply down. Not will be found to be down, is down, definitely. As a fact about the world, hours before any light-speed message from Alice could arrive to say so. The correlations themselves are not in dispute. Experiment has confirmed them past all doubt, including with detectors far enough apart that no light signal could coordinate the outcomes. What is in dispute is the story of the choosing, whether anything actually happened at Bob's bottle, and if so, when, and in whose slicing of space-time. The mathematics of the standard theory, with its observer-triggered collapse, is permitted to shrug at these questions. A physical collapse theory is not. The standard escape, honored in every textbook, is to notice that no message actually gets through. Alice's outcome is random. She cannot choose whether her particle says up or down, so she cannot spell out words in the collapses. Bob, examining his particle alone, sees a fair coin, up half the time, down half the time, indistinguishable from noise, until Alice's results arrive later, by ordinary slower-than-light channels, and the correlation stands revealed. The prohibition, formally, survives. No signal, no paradox. Case closed for all practical purposes. But you know by now how this channel, and Penrose, regard that phrase. If collapse is physics, a real event in the world, not a bookkeeping update in an observer's notebook, then it is not enough that the violation stays unusable. The event itself must fit inside space-time somehow. It must happen in some lawful pattern, and any pattern painted across a single instant is painted across somebody's now and not somebody else's. The puzzle is not whether collapse can send telegrams. It cannot. The puzzle is what geometry the choosing itself traces through space-time. And on this question, nearly every collapse proposal ever offered has simply looked away. Penrose does not look away. His answer, sketched in correspondence and in the preface of his later editions, offered with full awareness of how it sounds, is that the collapse propagates along the past light cone. Sit with the shape of that. The light cone of an event is the set of all points that light could reach from it, the future cone, and all points from which light could have reached it, the past cone. Influences, by the constitution, travel forward, within the future cone. Penrose proposes that the accounting of a quantum collapse travels the other way. When the choice finally happens, its bookkeeping runs backward along the past cone, down the entangled system's own history, back to the event where the superposition was created, the source that emitted the two particles, the beam splitter that divided the paths. The choice, in effect, is entered into the ledger at the origin, retroactively. From that vantage, there was never a moment when one branch had collapsed and the other had not yet heard the news. The entire correlated history, from creation onward, is consistent with the single surviving outcome. Alice's measurement does not send a forbidden pulse across space to Bob's particle. It reaches back down the shared past, and the shared past reaches forward, lawfully, slower than light, to both of them. What could be crazier than that? Penrose asks. His own phrase, delivered with evident enjoyment, and the honest answer is, almost nothing, except every alternative. Instantaneous collapse breaks relativity outright. Preferred frame collapse smuggles back the universal now that Einstein abolished. The retrocausal ledger, for all its strangeness, is the one shape of choosing that fits inside the constitution without tearing it. No signal outruns light. No frame is anointed. No observer's now is privileged. The craziest sounding answer is the only one that keeps Einstein's law intact everywhere. Something must still be protected, though. If the past can be written into, even in this austere, bookkeeping sense, what stops a clever engineer from exploiting it? Why can Bob not examine his particle, extract what Alice's choice retro-wrote into their shared history, and receive her message before light could carry it? Here Penrose leans on a distinction he traces, with a certain mischief, to Einstein himself. The difference between what can be confirmed about a quantum state and what can be ascertained from it. Einstein's own criterion held that if you can predict a measurement's outcome with certainty, without disturbing the system, you have identified an element of reality. Penrose accepts the criterion, but notices what kind of reality it certifies. A quantum state answers only the questions it was prepared to answer. Prepare a spin pointing along a chosen axis. Ask it yes or no along that axis, and it answers with perfect reliability. That much is real, confirmable, Einstein approved. But ask the state the question you actually want answered. Which way are you spinning? And, in Penrose's delighted phrasing, it just looks at you blankly. I don't answer questions like that, it says. Give me a better question. Bob's particle, carrying the retro-written correlation, is exactly such a state. The right question would reveal everything, but nature declines to tell Bob which question is the right one, and no experiment he can perform will extract it. He sees his fair coin, nothing more. Quantum reality, in Penrose's language, can be confirmed but never ascertained. It will verify what you already lawfully know, and volunteer nothing. The prohibition holds, not because the world contains no faster-than-light bookkeeping, but because the world is discreet about it. Reality keeps two sets of books, and shows any given observer only one. Step back and appreciate the irony, because it is the structural joke at the center of tonight, and it tells you what kind of revolutionary Penrose actually is. Here is a man prepared to stand in a lecture hall and pronounce quantum mechanics, the most successful theory in history, wrong. And yet watch what he does the moment his own proposal brushes against Einstein's relativity. He contorts it, gladly, into the one shape, retrocausal, discrete, strange beyond easy telling, that leaves relativity untouched, unbent, sovereign in every frame. He will break the perfect theory before he will scratch the other one. That is not stubbornness. It is the entire thesis of the night in miniature. In the collision between the towers, Penrose has chosen his loyalty, and his loyalty is to the geometry, to the theory whose principles, he believes, run deeper than the recipe that outscores it in the laboratory. The ledger is to be amended, the stage is to be trusted. Einstein's constitution is not merely spared by his proposal, it is the referee his proposal was redesigned, at real cost in strangeness, to obey. Of course, the universe has never once cared where a physicist's loyalty lies. Every idea in tonight's story, the torn stage, the gravitational tax, the lifetime of a speck's bothness, the discrete retrocausal ledger, remains, as we say it, a proposal, precise, parameter-free, beautiful in its economy, and unproven. What separates this proposal from a century of interpretive philosophy is a single, wonderful, uncomfortable fact. It makes a prediction, a definite one. Superpositions of sufficient mass must die on schedule, at a rate no ordinary decoherence explains, everywhere, always. And a prediction with a number on it is an invitation with an address on it. Around the world, at this hour, in basements colder than deep space, and quieter than any place humans have ever made, a handful of experiments are converging on that address, climbing toward the country of the specks, where H bar over E sub G finally comes out of hiding. One of them has already returned a verdict of sorts, from beneath a mountain in Italy. It is time to visit the border while the guards are changing. Science owes its self-respect to a simple habit. When a beautiful idea makes a definite claim, somebody builds a machine to embarrass it. The DOC Penrose proposal makes a definite claim: mass superpositions decay, on a schedule set by gravity, and the machines are being built. The hunt has two strategies, as different in temperament as the towers themselves. One listens for a side effect of collapse in ordinary matter, patiently, in the quietest places on Earth. The other tries to force the confrontation directly, to build a superposition heavy enough that gravity must show its hand on a laboratory timescale. Both are underway tonight. One has already drawn blood. The listening strategy has a specific target. In the mathematically explicit versions of gravitational collapse, the equations DOC wrote down, which make the idea calculable, the collapse process comes with a side effect. It jiggles. A wave function being spontaneously localized, over and over, acquires tiny random kicks, and charged particles receiving random kicks must radiate, a faint, ceaseless whisper of X-ray photons rising from ordinary matter, whether anyone measures anything or not. Find that whisper, at the predicted rate, and gravitational collapse is discovered. We told the full story of this search on another night, so tonight we give it one paragraph, but the paragraph matters. Deep beneath the Gran Sasso Massif in Italy, under 1,400 meters of rock that screen out the cosmic noise of the sky, physicists installed a germanium detector of exquisite purity and simply listened, for months, for radiation with no ordinary source. The mountain stayed silent. No excess whisper appeared, and the silence was loud enough to rule out the simplest, most natural version of the DOC collapse mechanism, the parameter-free version, with its cutoff set at the scale of an atomic nucleus. That is a real wound, honestly reported. But note precisely where it landed. What the mountain refuted is the variant in which collapse continuously jiggles and heats the world. Penrose's own response, delivered in the interview with the calm of a man who had said so all along, is that the heating was never his. Bodies spontaneously warming themselves out of the gravitational ledger is, he says, exactly what should not happen, and the version of collapse he believes in, one that respects the conservation of energy over the long run, with the retrocausal bookkeeping we met in the last part, predicts no whisper for the mountain to hear. Critics may fairly reply that his version is not yet a fully explicit theory that can be fed into a detector's forecast. He would agree, and has said in as many words that what he has is a problem, and a formula, in search of a theory. The mountain has narrowed the family. The head of the family remains at large, which is why the second strategy, the direct assault, is the one Penrose himself has always favoured, and the one converging on the country of the specks. Its modern blueprint was drawn in 2003, in a proposal Penrose co-authored with the physicists William Marshall, Christoph Simon, and Dirk Boomeister, and its elegance deserves a slow description. Take a tiny mirror, a wafer, perhaps 1/10 of a millimeter across, trillions of atoms, enormously heavier than anything on the interference staircase. Send a single photon at a beam splitter, so the photon enters a superposition, transmitted down one arm, reflected down the other. In one arm, the photon strikes the tiny mirror and nudges it. An almost immeasurably small push, but real. The photon's bothness now infects the mirror, struck and recoiling in one branch, untouched in the other. A massive object has been placed, indirectly but genuinely, into a superposition of two positions. Now hold the arrangement, let the mirror swing on its mount, and bring the photon's paths back together. If the ledger's law survives at this mass, the recombined photon will interfere with itself. The stripes will be there, the signature of an unbroken superposition. But if something objective collapsed the mirror's bothness while it hung suspended, something with, say, a lifetime of h bar over E sub g, the photon's coherence dies with it, and the stripes wash out at exactly the rate the formula commands. The experiment is a trap for the chooser, a superposition heavy enough to owe gravity's tax, and an interferometer positioned to watch the payment happen. The trap's cleverest feature is the one that answers the obvious objection. A skeptic will say, coherence dies in every big experiment anyway. Decoherence, the shredding by the environment, kills the stripes long before any exotic mechanism needs to. How would you ever know which assassin did it? The answer is that the two assassins keep different schedules and obey different laws. Decoherence rates depend on temperature, on gas pressure, on scattered photons, on every knob the experimenter controls, and they can be calculated, measured, and beaten down, decade by decade, with better vacuums and deeper cold. The gravitational lifetime depends on none of those knobs. It depends only on the mass distribution and the separation, h bar over E sub g, indifferent to how clean your chamber is. So the strategy is not to eliminate decoherence entirely, which is impossible, but to drive it below the gravitational rate. Build an apparatus so quiet that ordinary physics predicts the stripes should survive for, say, a full second, and then watch them die in 1/10 of that, on gravity's schedule, with every knob at its cleanest setting. A death with no assassin left standing but one. That is what discovery would look like in this field. Not a flash, but an unexplained punctuality. Building that trap has consumed 2 decades and is not finished, because the engineering demands are close to unreasonable. Mirror vibrations must be frozen to the quantum ground state, stray gas molecules eliminated, thermal photons starved. The whole apparatus held colder and stiller than anything in the natural universe. But the campaign has been advancing along a broad front, and you have already met its vanguard. The levitated nanospheres, glass beads a thousandth the width of a hair, held in vacuum on a pinpoint of laser light, their motion cooled in 2020 to the quantum ground state, are exactly this program's building blocks, massive by quantum standards, isolated from every environment, awaiting the protocols that will ease them into spatial superpositions and watch for an unexplained death of coherence. The matter wave interferometers that set the 2025 record, 7,000 atoms, 170,000 mass units, are the same campaign from the other flank, climbing the staircase rung by rung with the border, now, for the first time, a named destination rather than a fog. And for the final assault, there are designs that leave the planet entirely. A proposed space mission, the concept is called macro, that would release nanoparticles into superposition in the microgravity and near-perfect vacuum behind a sunshield in deep space where free fall is unlimited and nothing shakes, and let their bothness age for the seconds and minutes that no terrestrial trap can offer. Honesty requires the deflating number alongside the thrilling ones. Superpositions whose gravitational lifetime is measured in seconds sit near the Planck mass, around 100,000th of a gram, still roughly 14 powers of 10 beyond the current interference record. Nobody will trap a Schrödinger pebble this decade, but the formula's predictions bend downward to meet the climbers. Make the object denser, the separation cleverer, the isolation longer, and detectable deviations from the flat ledger creep within reach of instruments now on drawing boards. For the first time since the founding generation shrugged, the missing verb has a mailing address, and mail is being sent. Come stand in one of these laboratories for a moment, because the temperament of this frontier is unlike anything else in physics. The room is dark, and most of it is plumbing for cold. At the center, inside a steel chamber pumped to a vacuum emptier than the space between planets, a bead of glass, smaller than a bacterium, hangs on a waste of focused light. Hangs, not rests, touched by nothing material at all. Its trembling has been cooled away layer by layer, until what remains is the irreducible quantum shiver that no refrigerator can remove, the zero-point motion, the floor of the world. Instruments watch it through the chamber windows with the attention of a hospital. Tonight's run, like last night's, like next month's, will tease the trap open, soften the light, let the bead's wave function breathe outward, invite it, gently, to be a little bit here and a little bit there at once, while the detectors listen for the one thing this room was built to hear: coherence, dying faster than any known noise can kill it. The signature of the tax collector, gravity, arriving to disallow the arrangement. Most nights, every night so far, the ledger holds, and the bead keeps its ghost. The physicists go home, recalibrate, subtract another whisper of noise, and try again, slightly heavier. It is slow, unglamorous, magnificent work. The direct interrogation of the border between the quantum world and this one, conducted one photon of patience at a time, in rooms where the loudest sound is the future, arriving quietly. So the situation, as you drift, is this. A formula with no free parameters stands accused of being the missing verb of physics. One family of its relatives has been executed under a mountain in Italy. The direct trial is under construction on 3 continents, and, perhaps, one day, behind a sunshield, 1.5 million kilometers from here. No verdict has been returned, and none is imminent. The honest horizon is decades. But a verdict is coming. This is now engineering, not metaphysics. And when it arrives, it will land on one tower or the other. Either the ledger survives at masses where gravity swore it could not, or a superposition dies on Einstein's schedule, and the perfect theory is caught, at last, in its first lie. Which brings us, in the quiet at the end of the night, to the only question left. The one the title of tonight's journey has been holding open for 2 hours. 2 perfect theories, 1 contradiction, sitting on a tabletop. When the universe finally answers, which one breaks? Every long journey through a contradiction ends at a fork with 3 roads, and we owe it to the night to walk a little way down each before we let Penrose choose. The first road says, nothing breaks. The ledger is exact, superposition never dies, and the appearance of a single definite world is the greatest illusion ever staged. This is the many worlds road, and it is walked today by serious, first-rate physicists. We gave it a full evening of its own once, and it earned it. Its price is the totality, every quantum alternative real, every outcome inhabited, reality branching without end. Penrose's dissent is not squeamishness about extravagance. He has, after all, proposed stranger furniture than extra worlds. His dissent is that the road does not actually reach its destination. Quantum mechanics, he points out, doesn't say anything about many worlds. The branching picture must still smuggle in extra rules to explain why experience tracks one thread and why the threads obey the Born rule's exact probabilities. The very facts the road was paved to explain. And beneath the technical complaint sits a older loyalty, stated in a single sentence that may be the most Penrose thing he has ever said. I want to go the way that the world goes. The world, as presented to every observer who has ever lived, goes definitely. A theory that cannot recover that fact without whispered amendments has not, in his view, earned the right to multiply universes in its defense. The second road says, quantum mechanics is exact, and it is gravity that must be rebuilt, quantized, hauled into the ledger, its geometry dissolved into some deeper quantum substrate from which spacetime merely emerges. This is the road of the 90-year program we surveyed at the midpoint of the night, non-renormalizable at every naive attempt, its leading framework in a crisis its own founders now describe in public, its rivals elegant and unconfirmed, and the entire enterprise without one measured prediction to its name, through no lack of brilliance, but because the answers are locked behind the Planck wall, 15 powers of 10 beyond our finest machines. It may still be the true road. Most working physicists, if pressed, would still bet on it. But after 90 years, it is fair to say the road has not moved, and that its central assumption, that in any quarrel between the towers, the ledger outranks the stage, was inherited rather than argued. And the third road is tonight's, both theories are magnificent, both are approximations, and the seam between them is exactly where the second tower's missing verb has been hiding. Gravitize quantum mechanics. Keep Einstein's geometry sovereign. Amend the ledger's smooth linear law with the one term it always lacked, the gravitational self-energy of ambiguity, h bar over E sub g, the tax that makes electrons immortal ghosts and dust motes decisive citizens. On this road, the Schrödinger equation joins a distinguished retirement community. Newton's gravity lives there too, not wrong so much as bounded, a flawless servant within its domain, superseded at the edges by something deeper. On this road, the measurement problem was never a paradox of philosophy. It was a signal, a century-long anomaly, pointing, like Mercury's stubborn orbit once pointed, at the exact place where the next theory begins. Weigh the 3 roads one last time, not as slogans but as wagers, because that is what they are. The first road bets that the strangest bookkeeping in science is the literal architecture of reality, and pays for its tidiness in worlds. The second bets that 90 years of structural failure is a run of bad luck, and that the answers wait, intact, behind a wall we may need centuries to scale. The third bets that the wall is a message, that the failures of quantum gravity and the scandal of measurement are not 2 problems but one, a single seam photographed from opposite sides. Only the third road, note, has the manners to be refutable soon. It names a mass, a timescale, a laboratory signature. The first 2 roads can absorb any conceivable experiment without flinching, which is a kind of strength and a kind of warning. Physics has usually advanced by backing the wager that could lose. You have known for 2 hours which road Penrose walks. Hear now how bluntly he names it. Quantum theory as a whole, he says, is wrong. Not incomplete, wrong, and when the politeness of the founders is invoked against him, he dismantles the politeness with a smile. Einstein and Schrödinger said incomplete, but incomplete means wrong. Incomplete is a more polite way of saying it's wrong. He is, by his own cheerful confession, being rude, and he extends the courtesy of honesty to the theory itself. It doesn't mind people like me being rude to it, he says. It's pretty robust. There is a lovely symmetry hiding in that joke, one worth taking with you towards sleep. All night we have watched nature itself practice a kind of courteous refusal, the spin that will not say which way it points. Only I don't answer questions like that. Give me a better question. Physics, Penrose believes, has spent a century asking quantum mechanics to be the final theory, and the universe has been declining the question, politely, in laboratory after laboratory, waiting for us to ask a better one. His life's wager is that the better question is the one we built tonight. Not how do we force gravity into the ledger, but what does gravity already do to the ledger? And the answer, if he is right, is that it does the one thing the ledger never could. It chooses. He is in his mid-90s now. He shared the Nobel Prize at 89, for work he did at 34. He has outlived most of the generation he argued with, and he reports, with a comedian's timing, that age has not mellowed him. I've got more narrow-minded as I've got older, he says. And among the things he has grown narrow about is this: the collapse is real, it is gravitational, and the experiments will bear him out. He may not be there when they do. The honest horizon for a direct verdict is decades. The levitated beads and the folded space missions will do their patient work on their own schedule, indifferent to birthdays. Something in that arithmetic refuses to be sad. Galileo never learned what the falling sphere of sparks was actually telling him. That free fall erases gravity, because gravity is the shape of the world. The answer arrived 3 centuries after his death, in the happiest thought of a patent clerk. 4 centuries of watching things fall, and each generation's unfinished question became the next one's foundation. An old man betting his last decades on the universe's honesty, with the verdict due after he has gone, is not a tragedy in that tradition. It is the tradition. So let us end where the night began, with the 2 perfect theories. But you are no longer the person who began it. You know now that the perfection was always a truce, that beneath the trillion decimal scorecards, the theory of the large and the theory of the small have been contradicting each other all along, not at the edge of a black hole, but on the surface of every table. That the contradiction has a size, an energy, a lifetime, a number you could almost write on a grain of dust. Physics' 2 best theories contradict each other, and one of them has to break. Perhaps it is Einstein's. Perhaps the ledger holds at every mass, the worlds multiply, and the geometry dissolves into something stranger beneath. But if the man who mapped the black holes is right, the theory that breaks will be the perfect one, the one in your pocket, the one that never missed, caught at last by the oldest force there is, in the country of the specks, paying a tax it never knew it owed. Either way, the universe has already decided. The answer is written into every unwatched speck of dust that quietly settles, somewhere, into exactly one place. We are only waiting to be told. Thank you for spending this night with the 2 great theories, and with the quiet argument between them. If explorations like this one are how you like to end your days, a like or a subscription would mean a great deal to me. It is a small gesture, and it genuinely keeps these long nights possible. And remember, the next time you set a glass on a table and it simply stays, solid and single and certain, you may be watching gravity quietly win an argument, a century old. Good night, and may you never look at a speck of dust the same way again.